The next part of this introduction is the area of heat transfer. So all I'm going to do is give you a very brief overview of the different modes of heat transfer and how these are the equations that are provided to predict conduction, convection, and radiation can be used in order to assess the behavior of a thermal system from a very high level. So for the moment, it's just an introduction, and we're reviewing essentially material that would have been covered in second year. So it's a review. The modes of heat transfers are conduction, convection, and radiation. Conduction happens through a solid medium. Convection involves fluid motion, and radiation doesn't require any matter in order to take place. That is, the transfer is happening through transfer by electromagnetic waves. So the conduction itself, the way we're going to model it is by using Fourier's law of conductive heat transfer. And we're going to pay particular attention to one-dimensional heat flow. That is, heat flow through a one-dimensional structure, which means that the heat or the temperature will vary only along one direction. And typically, we're going to look at planar wall, that is, walls with two surfaces that are planar and parallel to each other. One-dimensional heat flow means that there is one temperature which is the same at any point along one of the surfaces perpendicular to the direction of heat flow. So temperature T1 is the same everywhere along the left, T2 is the same everywhere along the right. If T1 is greater than T2, then we will have heat transfer by conduction due to the non-equilibrium in temperature distribution. That is, physics always attempts to reestablish equilibrium, and because of the higher temperature on one side than the other, there is a higher amount of thermal energy on the left, and heat will flow from the left to the right in order to attempt to restore equilibrium. Convection also happens when you have an area in your physical domain which is at different temperature than the other one. But in that case, what you need to have in order to get convection is a fluid which interacts with a solid surface. So the heat transfer happens between the surface and the fluid, and the direction of heat flow, which is shown here by the red arrow to go from the surface to the fluid, will depend on which area or which part of the domain is at a higher temperature. So if the wall temperature Ts, as for surface, is higher than the fluid temperature written T infinite, then the heat flows from the wall to the fluid. So the nomenclature here, T infinite means sufficiently far from the surface in order not to feel the effect of the surface. So it's what we call the free stream temperature, well away from the disturbance, which is due to the wall. Radiation happens between two surfaces without necessarily any material in between the two surfaces, and essentially heat radiates in all directions. Doesn't necessarily mean you have the same amount of heat flowing in this direction and in this one, and we'll see how to deal with that towards the end of this presentation. So conduction, how do we model it? With this vector equation, that is the rate of heat flow, which is written Q in heat transfer. A Q lower form Q is a vector, so that means it embodies both magnitude and direction. So heat flows in a specific direction, which is essentially the direction of greatest temperature decrease. If you have a one-dimensional problem, all the wall on the left is at a uniform temperature and all the wall on the right is at a uniform temperature, then the heat flows in the direction of greatest decrease in temperature, that is direction perpendicular to the wall. You could travel along a slanted line, but essentially you would go through a slower gradient or slower rate of decrease in the temperature. We want to go in the direction of greatest decrease, and that's perpendicular to the wall. So that piece of information is captured within a mathematical operator called the gradient operator. So if you apply the gradient operator to the temperature variable, then you get a vector That is a quantity or mathematical entity that carries both information of magnitude and direction. Direction is the greatest increase in the temperature. So to get the direction of greatest decrease, you just put a minus sign in front. So the gradient, mathematical operator gradient, points in the greatest, in the direction of greatest increase in the variable it operates on. And the magnitude of the gradient is essentially the rate of change of that quantity with respect to space. So generally rate is used with respect to time, but in that case, I mean the rate of change of the temperature with respect to space. So if it's one-dimensional, temperature only varies in the direction x. Therefore, the gradient is going to be dt over dx. Okay, so that's what we see here. So let's talk a little bit about that. A different notation for the rate of heat transfer. So Fourier's law of conductive heat transfer is what we have right here. Q, rate of heat transfer, is proportional to this quantity, which is the exact same as this. That is, this is the gradient of temperature. It's a vector. We've just discussed that. But it's also proportional to the area. The greater the area of the surface through which the heat is transferring, you see that that vector, the red arrow, is actually perpendicular to the gray surface, and it's the direction of heat flow. And the greater that surface area, the more heat you're allowing through for a given temperature difference. So that's why area is important. And when we say Q is proportional to the area and the gradient, then essentially we mean that we can say Q is equal to the area times the gradient multiplied by a coefficient of proportionality. That coefficient of proportionality, just as we were talking about viscosity being a coefficient of proportionality, in this case, we talk about thermal conductivity coefficient. And it's a transport quantity because it essentially measures the transport of heat per unit time. Units. Q is measured in watts. Watt is joule per second. That is an amount of energy per second. We have an alternative notation for Q here, which is Q dash dash, which is a heat flux vector. And the meaning of heat flux is simply rate of heat transfer divided by area. So Q is equal to flux multiplied by the area. So if you know the rate of heat flux through a surface, if you know the rate of heat transfer through a surface of area A, you simply divide that Q by A to get the flux. It means the units of the flux is watt per meter square. It's rate of heat flow divided by area. K, you can get the units simply by dividing Q, or the units of Q, by units of A and the units of gradient of temperature. A gradient is defined, the easiest way to look at it is in one dimension. It's dt over dx. It's the first derivative of temperature with the space dimension x within the dimension where, or the direction where temperature changes. So essentially the units would be temperature divided by distance. Temperature divided by distance, so it's K divided by meters. So to get the units of K, you take watts divided by meter square divided by K divided by M. So the meter square is divided by M, so that's why we only have an M. You can write it down and you'll see the derivation of the units. We'll do that on paper at some stage. So that's the definition of rate of heat transfer in one direction. So in the direction perpendicular to the wall, we can define that direction as x, and then we write essentially Q dash dash, the flux vector, is equal to minus K times dt over dx multiplied by the unit base vector I in the direction x. Okay, I is a vector. So essentially, if you multiply all that by I, you get the flux vector. If Q dash dash is negative, let's go back to the previous slides, it means this vector is in the opposite direction to the vector I. I points in the same direction as increasing x. Therefore, if this is negative, heat flows in this direction. If Q dash dash is positive, heat flows in the same direction as I, that is to the right. That's what we have here. Okay, so Q dash dash to the left, or to the decreasing x, you understand that arrow, meaning this is the direction of increasing x. So if Q dash dash is negative, it goes in the opposite direction, and that's what's discussed, and that's what I just mentioned. So that's for one dimensional. If you don't want to deal with vectors, you can use a non-vector notation, which just gives you the magnitude of Q. So that's K times A times delta T over L. Delta T is the temperature difference across, and L is the thickness of the wall. If you don't use vector notations, you have to then say which direction the heat flows in. So if, in English, you simply state the heat flows from the left to the right or in the direction of increasing X. What about 3-dimension? We did say that, well, sometime I'm going to give the definition Q or in Q dash dash. You know, the difference is just that you need to multiply this by the area A to get the rate of heat transfer. Q dash dash is defined as minus K times the gradient of temperature. The gradient of temperature in 3-dimension is written like this. So it's the temperature change, or the rate of temperature change with respect to X, to Y, and to Z. Temperature, therefore, is a function of X, Y, and Z, so that the derivative must be written as partial derivatives. Okay. Physically, it's quite simple. The vector Q dash dash needs to be perpendicular to what we call the isotherm. The isotherms are contours, so curved surfaces, over which the temperature is constant. Just like you think of isocontour when you climb a mountain, the direction of steepest ascent is the direction perpendicular to the contour. If you were to go along the contour, temperature doesn't change. So that's the direction of no change in temperature. The direction of greatest change is the one that's directly perpendicular to that isotherm. So physical interpretation, if you were able to map the temperature everywhere in space, you would be able to draw those isocontour, that is lines or curves, like curves in 3D and lines in 2-dimensional, which have the same temperature anywhere along. So if you sit on that curve and you see how the contour evolves, you can see which direction is perpendicular to that, and you know where the heat will flow. That's the beauty of that gradient operator. That's what it tells us, the direction of greatest increase. Because heat flows in the decrease, in the direction of the greatest decrease, then you put a minus sign to mean the opposite direction. The minus doesn't change the magnitude, just changes the direction. Right, so and the only thing left to know is the conductivity, or the thermal conductivity coefficient. K is a property of the material. Different material have different conductivity, and it will not be a surprise to you, imagine, that metals such as copper, for example, have the highest conductivity, whereas gases have a very low conductivity, and they are actually used for insulation in some double glazed window design. Okay, so you can have a sense of the scale there. We have a semi-log scale. Convection. So there's just one video there for convection heat transfer to give you a sense of what it means. We're talking about fluid, perhaps that's colder. Let's say the blue is colder than the surface, which is red. So the cold fluid is interacting with a slowly growing thermal boundary layer, so a layer of fluid near the walls, which are heated up by the hot walls. So that cold fluid is really disrupting that boundary layer, that is a thin layer near the walls. And it's bringing cold fluid in contact with the wall. And that cold fluid affects very high heat transfer. If you were sitting there and you were nicely at the red, that is, let's say 30 degrees Celsius, and you've got cold air at 0 blowing, clearly if you're here or here, you'll feel very cold. If you're here, you'll feel warm. And you see these regions of cold move, very dynamic. And that's the reality of fluid flow. It's never, almost never in reality stationary, but it also moves all the time, and it can move with very large difference in terms of scales in time and space. Okay, so things can move fast, quickly, or slowly, and it can be difficult to predict. Okay, so that's what convection is. So using a very simple formula like the conduction is not necessarily available. We don't have the luxury of something that simple. The reality is that convective heat transfer will change, but as an engineer, that's not very useful. So it's good to have a simplified formula. And that's Newton's law of cooling. We can still define heat flux, or if you wanted rate of heat transfer, you'd simply multiply all that by the area over which the heat is being transferred. So the flux locally at a point would be the local value of the convection heat transfer and the temperature difference. we could determine that from experiments, for example. Typically, it varies continuously over space and time. It's generally impossible to predict with great accuracy, but we can predict how, on average, it will behave, either average over space or time, or over small regions of space. So we don't really use a vector anymore because heat transfer may be perpendicular or it may be in this direction, that direction. We can't say. What we know is whether the heat will leave the surface to go to the fluid or the fluid to the surface. Generally can be worked out with different type of convection. So we're talking about convection here. Fluid motion affecting heat transfer. This is convection. We have forced convection, free convection, mixed convection, and we have convection with phase change. We're not going to study this, phase change being boiling and condensation. We're dropping this and this from this course because of the shorter semester, and we're going to focus on the forced convection. Forced convection is when there's an external forcing mechanism that forces the fluid motion in order to effect stronger heat transfer. The natural convection is what would happen if you were just heating the fluid or cooling it down, and as such driving a density change in the fluid. If you, for example, heat up air, then the air becomes lighter and starts rising up, and that's what we call natural convection. We're not using a mechanical means to force the airflow. If you've got both, you have the mixed. So here, this year, we're going to focus just on the forced convection. The non-vector notation, we just have to tell the story, essentially say when we're solving a problem in which direction the heat flows. Sometimes we don't know at the beginning, so we make an assumption, and the sign of the heat flux or heat rate of heat flow we get is going to tell us whether that initial assumption was right. If it's negative, it means your assumption was wrong. The heat flow was in the opposite direction. So if you say the heat flow is from the surface in red to the fluid in blue, means the heat flows from there to the fluid, and we write the equation, Newton's law of convective cooling, by putting the temperature of the surface first minus the temperature of the fluid. So that means we assume the heat flows from the surface to the fluid. And that is the case if temperature of the surface is higher than temperature of the fluid. Therefore, we should get a quantity which is positive. H is always going to be positive by definition. So if it's the opposite, you change the direction in order to ensure that all this remains positive. So this is just a schematic representation of what happens. If you've got fluid flow above the plate, then you've got a gradient in temperature. We have what is called a no-slip boundary condition, which guarantees that the fluid particles right at the wall will take the same velocity as the wall itself. As you move away, if the fluid goes faster above, then you have a gradual transition. The temperature behaves in a similar manner. That is, if you have a temperature difference across, you'll have a gradual difference in or transition from the temperature of the surface to the fluid. And all these changes are taking place in what we call a boundary layer. That is a layer of fluid which is near the solid boundary. Oops. And we have different thickness of these layers. Generally, we say that the thickness is defined as the size of the boundary layer over which 99% of the changes are happening. So outside of it, we assume no influence of the plate, and we recover the free stream velocity. So that gives us the thickness of the hydrodynamic boundary layer, whereas on the thermal side, we have the thickness of the thermal boundary layer. We'll come back to all that later on. If you have internal flow rather than what we call external flow over a surface, so fluid flows over a surface externally, if it's happening inside a pipe or constrained domain, then the fluid or the heat will flow either from the fluid to the solid or the solid to the fluid. Nothing changed there, except we don't have anymore what we call the free stream temperature. Okay, previously, if we went sufficiently far from the surface, you had an undisturbed temperature, and we called it the free stream. Now, everywhere the temperature will be influenced. So instead of taking the temperature difference between the surface and the free stream, we take it from the surface to what we define as the mean temperature of the fluid. And that may change as you move along the x-axis, as you heat up the fluid, for example. We'll talk about this in the next movie. Just wanted to keep the movies short enough.